Hello and welcome everyone. Thank you for taking the time today to join us for our webinar titled Accelerate Your Model Training with H2O-3. My name is Patrick Moran. I'm on the marketing team here at H2O.ai, and I'd love to start off by introducing our speaker. Megan Kurka is a customer data scientist at H2O.ai. And now before I hand over to Megan, I'd like to go over the following housekeeping items. Please feel free to send us your questions throughout the session via the questions tab in your console. We'll be happy to answer them towards the end of the webinar. And this webinar is being recorded. A copy of the webinar recording and slide deck will be made available after the presentation is over. And now without further ado, I'd love to hand it over to Megan.
Hi everybody, hope you can hear me okay. Today we're going to be talking about accelerating your model training with H2O-3. And thanks Patrick for the introduction. So let me just go over the agenda for today and then we'll jump right in. So I'm gonna give a quick introduction to the H2O-3 software in case anyone's not familiar with it. And then we're probably just really gonna do a demo the rest of the time. We're gonna try using H2O-3 for exploratory analysis, using H2O-3 for feature engineering, model building, and finally, once we've chosen our model that we want to use in production, we're going to use it for model interpretability. So that's our four components for today's demo and discussion. And I'm really trying to focus on the full life cycle of the data scientist today. So that's what we're going to be talking about, and I'll start with just an introduction to H2O-3. We're going to leave about 10 minutes at the end for questions. So if you guys have any questions while I'm going through this webinar, please feel free to post the questions and we'll read them out at the end of the discussion. Okay. So the first is our H2O-3 overview. If you guys were at my last webinar, we talked a little bit about all of our open source and closed source products. Today we're just really going to be focusing on H2O-3, H2O open source on the left-hand side. So just going over what H2O-3 is, it's an in-memory distributed machine learning platform. All of our algorithms are written in distributed Java, and it's really built for a data scientist. So you might notice if you saw the last webinar with driverless AI that's very automated. Open source H2O-3 offers a lot of control. So it is geared towards a data scientist, and I'll show in today's demo how we can use H2O with Python in a Jupyter notebook. But we also have APIs with R, or what we call H2O Flow, which is our web-based UI, which I'll show too today. Right. What is H2O? I kind of gave a little bit of an introduction, but it is written in distributed Java. We have a bunch of different algorithms, supervised and unsupervised. So we have supervised algorithms to help predict a specific column in your data set. We have unsupervised algorithms, which is really geared more towards learning about your data. So are there anomalies in my data? Are there natural segments or clusters occurring in my data? So there are two kind of approaches that we both support in open source H2O-3. And as I mentioned, we do have the R, Python, and a web UI. The last thing I want to mention is, it is written in a parallelized and distributed algorithm, written in distributed Java. And what that does is it allows you to use your full data set for these types of, with this software. So let's say you have a use case where you maybe have a terabyte of data that you want to leverage the full data set with. H2O-3 can handle that because it can scale. H2O-3 can be run on top of Hadoop or Spark, for example, and leverage the power of that infrastructure to work on your full data set. So here's just a quick kind of example of what that setup could look like. So in this particular example, we have a Hadoop infrastructure here, and H2O is running on top of that. And it's essentially, if you're familiar with Hadoop, it's essentially a map-reduced job that never reduces. So it's just going to run on top of Hadoop, and then you can configure H2O how you'd like. You could have it run a single node, or 5 nodes, or 10 nodes, or however large you want this to be, depending on your data set size and your infrastructure. And then it'll allow you to work with your full data set, but still while connecting from Python or R. So we have this H2O cluster, and let me just walk through how it would feel like for a data scientist. As a data scientist, I've launched this H2O cluster somewhere, maybe on Hadoop, maybe on Spark, maybe in the cloud. But then I'm over here on my laptop. And what I can do is I can work from, in this case, R or Python or, the Flow UI on my computer. And basically, I'm going to tell the H2O cluster what to do from R or Python. So I'm still working where I'm familiar with it. I'm still in this case in RStudio, kind of writing code. It's my same environment that I'm used to. But it's sending REST API calls to the H2O cluster, and it's telling the H2O cluster to do something. So if anyone's on the call has worked with very large data, they may know that at some point they're not able to work with the full data set on their local computer. So while they can work with a lot, eventually they're going to have to sample down if they want to use R or Python on a single server or on their local computer. What H2O is allowing you to do is allowing you to, for Python or R, work on the full data set. So it's telling this H2O cluster with all this horsepower behind it to do something. And this H2O cluster with multiple machines or multiple JVMs, the data set is distributed across that cluster. And now I can tell H2O do a group by, or H2O add a new column for me. And more specifically, in what we really focus on, H2O build a model for me. And this is not requiring any sampling down. It can actually leverage the whole data set. And I'm still working from this client that I'm used to. So in today's demo, we're going to show how this works from Jupyter Notebook. And we're going to dive into kind of the typical workflow of a data scientist. So that's my introduction, my quick introduction to H2O-3. We're going to jump now over to my Jupyter Notebook, and we're going to go through a demo. Okay. All right, hopefully everyone can see the screen. We're going to do right now an Airbnb analysis in H2O-3. So I'm actually using the same data set from our last webinar. We're going to take a look at this public Airbnb data for New York City. And we're just going to go through the steps I mentioned before. We're going to first start out with data exploration, followed by feature engineering. We're going to build some models using our AutoML, which I'll talk more about later. And then finally, we're going to try to interpret what's going on with that model. All right, so we're going to start with starting up H2O. This is importing the H2O library and starting up the H2O cluster. Now, this is how you start it up if you'd like to run it from the local instance, or wherever you are, you want to start up a single instance of H2O with a single node. However, if you started this on a Hadoop or Spark or somewhere else, you would just connect to that H2O cluster. So you'd connect to the IP where it's running and port. And that will connect you to an H2O cluster that's running somewhere else, maybe with a lot more servers. But for this particular demo, we're going to run it locally. When I run the H2O init, it's going to tell me a little bit about this. It's going to tell me how long the cluster's been up, what cluster version I'm using, and how old this cluster version is. So this has been released 2 days ago, this new version. It's going to tell me how many nodes are in a cluster. So I'm just running this locally, so it's just a single node. It gives me a little bit of other information. But one thing you'll notice is it says connecting to H2O server at this location. Now I'm going to go and click on this. By clicking on this, I'm taken to a web UI. This is actually our point and click web interface for H2O-3. So here I can actually run through a machine learning workflow by clicking and clicking. So I can ask to import data, I can go to my model menu and ask it to build a model, or run AutoML, we can score with it, and so on. So Flow is really nice. Doesn't matter how you start H2O. If you start H2O from Hadoop in the command line, if you start H2O from R or Python, no matter where you start it, you'll always have access to H2O Flow. And you can use it in combination with one of the R or Python clients as well. So what we're going to do today is we're going to use Python mostly, but we're going to always go back to Flow because everything that's happening in H2O cluster can be seen from both Python and Flow. So we're going to kind of use both today to get a better sense of what our models look like. All right, I'm going to start by importing our data. Now I'm importing data from a local file system, but you can also import data from S3, or we can import data from HDFS, for example, by putting an HDFS symbol or prefix at the beginning of the path. It'll import directly from HDFS. So I've imported my data, and we can see kind of a description of the data. So we have the ID of the listing, the name. So this is a clean and quiet apartment home by the park. The ID of host and the host name. The neighborhood group, the actual neighborhood, latitude and longitude of the apartment or the listing, whether or not it's an entire home or apartment, a private room or a shared room, and then the price. And then we have a couple of other statistics about the listing. So how many nights are minimum to rent this particular listing? How many reviews have there been? When was the last review? How many reviews per month were there? How many listings does this host have? And then the availability. So how many days is it available of the year? Now, today we're going to try to build a model to predict the price of an Airbnb, but we're just going to start out by exploring the data. So let's just get a sense of what our data set looks like and go through that steps. So the first thing we're going to do is we're going to go over to H2O flow. And what I'm going to do is I'm going to ask it to list all my data frames. We can see that we have this AB New York City. This is our data set that we've imported. If I take a look here, I can see all of the columns in my data set that we were just looking at in Jupyter Notebook. And I can actually click and get more information. So we can say, like, how many records are there per neighborhood? Or how many records are there in a neighborhood group? So most of the Airbnb data is in Manhattan, that's Brooklyn, Queens, Bronx, and then a small amount in Staten Island. So again, even though I imported the data using the Python API, it's still visible from Flow. And the reason really is that nothing's actually happening in Python. So Python, I'm just seeing this head of this data, but there's actually no data in Python. All of the data is residing on this H2O cluster, which is scalable, which can handle large data. So Python is just the way for me to talk to H2O, and I don't have to worry about running out of memory in Python. So we're going to go back to Python again, and we're going to ask H2O to do some data exploration for me. So the first thing I'm going to do is I'm going to ask to see a summary, a data set. So here we're getting each column as a feature in the data, and we're starting to get some summary statistics. So here's the average latitude, minimum latitude, and maximum latitude, or sorry, vice versa. So we're starting to see what the data looks like. H2O has sent this command to run a summary on the data set, and it's just returning the results back in Python. Now, the next thing I'm going to do is I want to take a look at what the correlation is between the different numeric columns in my data set. So we have some numeric columns like price, the latitude and longitude, minimum number of nights available to rent. So what I'm going to do is I'm going to ask H2O again, calculate the correlations for the numeric columns in my data. So here I'm just saying, what are my numeric columns? And then calculate the correlations. So let's run this. Now we get a correlation matrix. And again, we didn't really need any data in Python, actually. So this is kind of nice that we can run this from Python, have it work on the large data, and just give me back the small matrix for the results. The next thing we can do is we can ask H2O to create some histograms. So first I'm going to say, H2O, give me a histogram of the number of listings for the host. So we can see that most of the listings, or most of the hosts, have a number of listings that are in this bucket pretty low, less than 50 at least. We can ask now H2O, instead of showing me the histogram of the raw calculated host listings, take a log of it. So let's use the log scale of the histogram. This information is sent to H2O cluster. It does the log of this column, and then it calculates the histogram for me. So those are the built-in graphics we have for the data set, this histogram, and we get the summary. But we might want to have some custom visualizations. And the idea to think about it is there are so many open source plotting libraries available in Python or R. How can we leverage those? Now, the main issue with these open source graphing libraries is that there's a limitation to how much data they can handle, because there's a limitation to how much, this Python instance can handle on my computer. So what we always think about is, how do we take this full data, extract the information that we're really interested in, and then graph it? Now, the first thing I'm going to do is, okay, well, maybe I want to do a graph of the average price per neighborhood group. So is there certain neighborhood groups where there's a certain boroughs where there's greater price than others? Now, that data itself is going to be small. It's only going to be 5 records, because we only have 5 boroughs in our data. So what I'm going to do is I'm going to say H2O, group by the neighborhood group, and calculate the mean price per group. And it gives you this really small frame. This small frame is fine for me to convert to a pandas data frame because Python can definitely handle a 5-record data frame. So now I've asked H2O to reduce the size of this data to just what I'm interested in. And then I'm going to ask H2O to convert this to a data frame, pandas data frame, and graph it, give me a bar graph using Plotly, which is just one of the many open source Python libraries available for graphing. So now I can see the average price is higher, most high for Manhattan, then Brooklyn, and then maybe Bronx, Queens, Staten Island are kind of similar. There are certain graphs, however, that we might not be able to clearly aggregate. So here we were just looking at what's the average price per neighborhood group. But we might want to do, let's say, a scatter plot or something else. So in rest of today's demo, what I'm going to try to do is I want to take a look at kind of where do these Airbnbs, where are they located? We have the latitude and longitude. You know, where is there kind of like a dense cluster of listings and where are they more spread out? If I want to graph all of my data with a scatter plot, that can be pretty hard to do because the points end up overlapping each other and you generally lose the natural shape of the data. So what we're going to do instead is we're going to ask H2O to run this H2O aggregator estimator. And we're going to say, reduce the size of my data to just about 500 records. And what this aggregator is going to do is really going to find natural clusters of data. It's going to reduce it in a way that's maybe a little smarter than random sampling so that I don't miss out on the shape. And now I have this small Airbnb data. And if we ask to get the dimensions, it's about 580 rows. This is easy to convert to a pandas data frame. So now again, I'm working with a small data set that I've taken back into Python that I can graph. But I never have to actually work with a full large data set size. So now I'm going to ask my Plotly to graph the latitude and longitude. And I can start doing things like moving the graph, zooming in. So we can see that there's kind of a cluster of listings in these two areas. And then over here. And we can really customize this so we can add whatever information we want. So that was a little bit about how we can explore data with H2O. And again, really the idea here is that we let H2O handle the hard work of working on all these rows of data. And then we pass in the information we want to visualize into Python and then take advantage of it, the other libraries available in Python. Now our goal today, now that we've done the feature engineering, the data exploration, is to build a model to predict price. So we saw in our first graph here, okay, Manhattan, there's definitely a price difference by neighborhood group. So probably that's important. I'm going to ask H2O to build some models. It has multiple algorithms available. We have XGBoost, GBM, linear models, random forest, deep learning, CoxPH. So we have a bunch of different algorithms that are available to predict a target column. The first thing we're going to do is we're going to see if we can clean up the data a little bit before we even start building a model. So is there anything we could do to improve the shape of this data to make it easier for a machine learning model to tell us the price? If you look again, here's the head of our data. It's really clean data, but there are a couple of things that maybe we could do to help. So one thing that we're going to do today is handle the name. Now, machine learning algorithms cannot inherently handle text columns. So this just looks like a string. This string is different than the string below it. They're not the same. It only really knows that. Yes, they're the same, or no, they're not the same. But there's a lot of information that we're getting here. So this cozy entire floor of brownstone might indicate that this is going to be more expensive than, you know, a small, maybe private room. So how do we leverage the information that's in the listing name? So what we can do is we can convert this to numbers. Machine learning models have a very easy time handling numbers. They understand that the numbers are close together or they're far apart. So what feature engineering kind of usually amounts to a lot of the times is how to take this raw data. It could be categorical, dates, text, and how do we convert that to just a numeric representation so that the model can actually use it. So how do we convert the cozy entire floor of brownstone to a list of numbers? One way we can do that is an algorithm called word-to-vec. Now, word-to-vec is really just doing what we just described. It's taking a word and converting it to a vector of numbers. It's an unsupervised learning algorithm, and it's going to just take these words and give us, as I mentioned, a numeric vector. So we're going to start by, doing that. And just a little bit about how it works is it's assuming that words that are, have similar, the same neighboring words are similar. So if this word A always has this word after it, and we see that same occurrence for word B, word A and word B must be similar or synonyms or somehow related. So let's go look at our name. The first thing we're going to do is we're going to tokenize it. Tokenize it just means we're going to take these texts and we're going to split it up so that each word is separated. We're not going to just tokenize it though. We're going to clean it up a little bit. We're going to make these all lowercase. And we're going to say, let's remove words that are stop words. And stop words are just words that are used all the time that don't really have a lot of meaning. So the, I, me, my. You can get a list of stop words in at the NLTK library in Python. And we're going to drop these as well because they don't really help us that much. In this case, we just want to look at, we want to remove these stop words and focus on the others. So here's my little function that I've written. And again, I'm writing a function in Python, but everything that's going to happen here is going to be just told to H2O. So the first thing I'm going to do is I'm going to split the sentences by word. I'm going to convert it to lowercase. We're going to remove any words that have one character only. We're going to remove any words with numbers in it. And then we're going to remove words with stop words. So it's going to do kind of a few different things. And we're going to run this. This is going to be done across the distributed frame, across the cluster. And the output is going to be all of these names kind of cleaned up for us. So clean, quiet, apartment, home. So you see by the park have been removed because those are stop words. And now we're going to ask H2O to create this word-to-vec model on my names. We'll see it being built. One of the things we can do with word-to-vec is, since it is using this kind of neighboring words approach, if they have similar neighboring words or synonyms, we can ask word-to-vec to find synonyms for us. And the synonyms are just looking at the word embeddings that were created by word-to-vec and figuring out which word has the most close word embedding. So if I take large, for example, what does word-to-vec think the 5 synonyms are? So word-to-vec thinks spacious, huge, always, enormous, Lower East Side. Those are all synonyms to large. And now this is just learning this from my data set. It doesn't have access to any other data or anything else. It's just looking at my data and seeing what was kind of in the same positioning in text or the listing. So spacious and huge kind of went hand in hand. You can also ask, what's a synonym for JFK? So it's an airport, LaGuardia, airports, LGA, another term for LaGuardia. So we can kind of use this as a sanity check to see, did it really find the meanings of the words like we thought it would? And so in this case, it looks like it found it pretty well. So what we're going to do now is we're going to say word-to-vec, transform my names into the word embeddings, and let's add those word embeddings to my original data. So I've just called word-to-vec transform and cbind, which is going to add these as new columns. So if we kind of go down, we'll see a C1, C2, C3, all of these new vectors. And these just represent that listing. All right, the next thing I'm going to do is I'm going to ask to run AutoML. So AutoML is an automatic tool for grid search and algorithm selection in open source H2O-3. So I'm just going to switch over to Flow quickly. We're going to look at the models we offer. So if we want to build a model to predict price, we have access to deep learning, random forest, gradient boosting machines, linear models, and XGBoost. And all of those can be used to predict price. Now the hard part is, which algorithm should I use? And then which parameters should I use for this algorithm? And that's not an easy question to answer because it's very data dependent. So it's not really obvious just by looking at your data to know what's going to be the best answer. Typically the only way to really know what's the best kind of model and settings for that model is to try different things. So what AutoML is going to do is it's going to take my data and it's going to run through my algorithms and it's going to do grid search for me, which is just going to try different parameters for these algorithms. And we do focus on the parameters that we see make the biggest impact. And we try settings that we see do pretty well for different data sets. So it's kind of like a smart grid search. We're going to focus on where we know it has impact and what we know does well. And what we'll get out is a leaderboard, a list of the models that have been built and how they performed. So I'm going to go back to our run AutoML. And here I'm just going to kind of set it up. So the X variable, or our predictors, are going to be all of the columns in my data set except ID, host name, name, and price. So ID is just the ID of the listing. It's not going to be helpful to us. Name, that name of the listing, we've already converted to our word embedding, so we don't need name anymore. We've already represented it in a different way. And host name, well, we have host ID, so we can assume that host name is not going to be important. It's kind of unnecessary. And we're going to set up H2O AutoML. We're going to call the project Airbnb word embeddings. And for the purposes of today's demo, we're going to say just run at least the most 5 models and just run it for at the most 5 minutes. And then we're going to ask it to sort our leaderboard by mean absolute error. So in this case, I'm going to try to reduce the mean absolute error, which means I want, on average, the error to be as little as possible with my predictions. We can set a seed for reproducibility purposes. And then we can say exclude algorithm. So if we don't want a specific algorithm to be run, we can exclude it. So as I mentioned, AutoML is going to do a bunch of different algorithms, XGBoost, linear models, random forest, VM. One of the things it also will do is it will do a stacked ensemble, which is going to combine the models together with the superlearner. Today we're going to exclude stacked ensemble for the purpose of the demo, but that is available. And we're just going to say AutoML train. And we'll see that it's in progress. What's nice is that we can go to Flow and see this being built, because everything that I'm doing from Python is happening on the H2O cluster, and I can see it in H2O Flow. So I'm going to go to look at the jobs. Here's my AutoML, that job that's running, and I can say view it. You can monitor this live. So we have a leaderboard with 1 model right now, whose mean absolute error is $104. And we can see that it's building a second XGBoost model, now it's 3rd. And as this goes on, it's going to keep refreshing as it gets better and better. So it's trying different XGBoost models. It's going to try linear models until it's hit that setting, the maximum runtime settings that we've required for this. One thing to note is that all these models are being run by default with cross-validation. So what the leaderboard is showing me is how well it's doing on holdout data that it's never seen before. In this case, we can see that we have a bunch of different models. We take a look at this model, XGBoost. We see the importance of the variables. So if the room type is the entire home or apartment, it's the most important features. Then private room, then longitude. And then we see the C's, where all of those word embeddings that represent our name. So anytime we build a model, whether it be from Python or R, we'll always be able to look at it from Flow. If we like this model, we can say download the model deployment package, which we call Mojo. So this is something that's completely independent of H2O-3 that can be deployed in production. So if we run the AutoML leaderboard and we say, okay, we really like this model, now we can just download this, which is just Java code, and put it right into production directly. We can look at all of the algorithms. So we can look at their GLM now. We can see the coefficients of the GLM. You can also see some information like the cross-validation metrics. How did it do on my cross-validation data? What's the R squared? What's the mean absolute error? What's the coefficients? So what are the neighborhood coefficients? So we can examine all the models in Flow, or we can also look at them in Python. We can ask to see the leaderboard in Python. Now, one of the things we might want to do is analyze a model, kind of a little bit more. We know that we have this certain model we've chosen after our AutoML, but how do we learn what makes it predict the price that it does? So that's our last section of this particular talk today. How do we interpret this model? We're going to spend a good amount of time on this. Okay. So the first thing we can do is we can call model varm plot. What this is doing is it's just telling me the variable importance for the model. So here's the most important variable, room type private room, for this model that I ran yesterday, for example. The second most important variable is availability 365. So we can start to see how the variables affect the prediction and which are the most important. And the way that we calculate variable importance depends on the algorithm, but for our gradient boosting machines, for example, it's basically if I split on this particular column, how much does it reduce our error? So if I split this column and it doesn't really reduce my error at all, it doesn't have that much importance. And if I never split on it, it has no importance. So here we can say room type private room, the most important. Now, just knowing Airbnb and understanding how it works, I can assume that if the room type is a private room versus a shared room or entire apartment, it's most likely going to reduce the price. So sharing a room with someone else is going to be cheaper than having my own room or having my own apartment. But I don't know that for sure. So one of the things that we can do is we can ask H2O to create something called a partial dependence plot. And we can do this by saying model, call partial dependence plot on this data that I have, my Airbnb data. And I'm asking it to do one of my columns room type. And what this is doing is it's pretty simple, but it's very helpful. It's just going to take my data, my Airbnb data, and it's going to say, what if everyone's home or apartment, what if everyone's room type, every listing's room type was entire home or apartment? If I made everyone's listing to have that room type, the average price would be $101. What if I made everyone's listing a shared room? If I made everyone's listing a shared room and I said, okay, H2O-3 predict on this new frame, the average prediction of price would be only $68. And if I did it again and I said, make everyone's listing have the room type private room, and I said H2O predict on this new frame, now the average price reduces even further to $49. And here we can see the graph of this. Entire home or apartment versus private room versus shared room. So the dots here are those means, the averages that we've calculated. And the bar is the standard deviation. So a wide bar, it does have a wide bar, meaning entire room versus private room versus shared room is not the only thing that's going to dictate what the price is. There are a lot of other things like location and maybe a little bit about the listing name. But there's definitely a strong relationship between the room type and price prediction. So it's unlikely, in this case, that a private room would be more than a shared, and then the entire home or apartment versus a shared room. Okay. The next thing I'm going to do is I'm going to say H2O, run the same partial dependence plot on availability 365, because we saw that that's the second most important feature. And what H2O-3 is going to do now is it's going to take my availability 365 and bin it. So it's going to say, what if everyone's availability 365 was 0? Replace everyone's value with 0, predict using our model, and calculate the average response. What if everyone's availability is 19? And it's going to go through these different bins and give me this average prediction. So it's very similar to what we just did for the categorical column. And we're going to get this kind of graph. So here we can see that the availability 365 doesn't really affect the prediction until it reaches about 350. Then we see there's a jump. Now this is kind of nice because you really get a sense, these graphs really tell you a sense of how this variable affects it. So with linear models, you'll see that there's this one coefficient. So availability 365 has this coefficient, so this relationship with our target. So it's always going to be a straight line because it's a linear model. With these nonlinear models like XGBoost or GBM or random forest, the relationship could be much different. It could go up or down, it could be flat and then go up like we're seeing. So we really get to see a little bit more nuances into how the model is making the predictions that it did. So availability 365 in this case doesn't really matter until it's above this 350 mark. Okay. Now these different techniques we've just went through, they're all ways in how to get a kind of a global view of our model. So globally, how does availability 365 affect the prediction? Globally, how does the room type affect the prediction? But what if we're interested in why the model predicted a specific price for a specific listing? What if we want to know it at a local level? Well, in that case, we have something called predict contributions. So if you're familiar with this is using Shapley contributions to generate what we call reason codes. And really what it's doing is it's going to tell us how each variable affected the prediction. You know, maybe the room type increased the prediction by $20. Maybe the neighborhood decreased prediction by $30. We're actually going to see these contributions, and they're going to add up to the price prediction. So by calling the model predict contributions on our data, we're now going to get a new frame. Here's our price, and here's the effect the different features had on this prediction. So we can see most of them are 0. We're going to go to the right a little bit. Here we go. So neighborhood Riverdale, whatever the fact that it was, whatever it was, neighborhood reduced it. We can kind of go through the variables. Now, if we go below, we can ask H2O and Python to kind of reformat this for us so we can get a better sense of how the model made the predictions that it did. So here I just made a little helper function that's going to take a record, run Shapley contributions on that record, convert it to a data frame, and then sort it by the absolute contributions. So I've just run this for my first record, and I can see that the room type reduced the price prediction by $25. The availability 365 increased it by $15, and so on. So we can actually now get a sense locally about how the price prediction is created. And if we look at our first Airbnb record that we're analyzing, can see, if we look at the room type, that the room type is a private room. So it was not an entire home or apartment. So the fact that it wasn't reduced the price by $25. The fact that it was a private room reduced it by $13. The fact that it wasn't in Manhattan reduced it by $7. So we can start to get a sense of how the prediction was generated on a low level. Okay. Now the last thing we're going to do is we're going to try to get now another kind of analysis or another insight into our model. So we saw locally, how do we figure out how the predictions were generated by Shapley. We also saw globally how different variables affected the predictions with our partial dependence plots. But we do want to see kind of a little bit more detail globally. So we're just looking at a single variable at each partial dependence plot, but it could be that there are multiple variables and how they interact is what's actually affecting the prediction. So what we're going to do is we're going to ask H2O to build a surrogate decision tree. What a surrogate decision tree is going to do is it's going to be a simple decision tree that's going to try to predict our price prediction from our AutoML model. So we're going to take our model and predict with our data and add as a new column. And we're going to ask H2O to build a single decision tree with a depth of 3. And it's going to try to predict this prediction. And the reason why we're going to do that is we're going to be able to see from the decision tree kind of what path does it take to get to a high prediction group or a low prediction group. So here we've built our decision tree. We've asked H2O to build the decision tree. And we're going to ask it now to build a picture of that decision tree. So here's just a helper code that's going to generate the tree image for me. And it's actually going to use that mojo that we talked about. The mojo itself can be visualized. And this function is just going to visualize it for me, make it easy. And I'm going to call it and I'm going to ask it to generate this decision tree. So let's see what we notice. The first thing we'll notice is that the most important split is this record, this variable that starts with C, C69. So this was actually one of our word embeddings, one of the embeddings that we used based on the name. That's the most important feature in this small surrogate tree. And if we look at the bottom, those leaf nodes, this is going to be the average prediction from the decision tree. So here on the right side, we see the top 3 most expensive groups. This is on average $190, $97, $112, and $131. You see some smaller price groups here like $58, $53, $48. So we can take a look at the tree to figure out what about these particular listings gives it a high price prediction versus low price prediction. Now this model, this decision tree, is very simple. It's not going to be as accurate as our original AutoML model, but it's simple, so it's interpretable. There's always going to be this trade-off. We can have a very accurate model that's going to be very complex, but it's going to be hard to understand. So this surrogate tree, while it may not be accurate enough for us to say, let's move this into production, it does give us some insight into what's really happening. So here we're going to use this to get insight into the high cost or high price segments of listings versus low price segments listings. The first thing we're going to do is we're going to traverse a tree to see what makes this segment so high. Well, the first thing is their C69 value is greater than 0.01. So we'll hold that off for a second. We don't really know what that means, C69 being high. We'll take a look at that in a second. The next thing is the entire room, the room type is entire home or apartment. So these are groups of listings where you're getting the entire home or apartment. And the last thing is it's available more than 361 days of the year. So it's available almost all the time. These listings are about, on average, $197 based on the AutoML model. This is the average prediction from our AutoML models. We can see another group here with pretty high value. Let's take a look at this. So this is where C69 is low, but now C12 is high. C12 is another one of our word embeddings. And the room type is not a private room. So here's another kind of hotspot for high value or high cost, high price listings. So it makes sense to me that the private room versus the entire room would have price differences. And we can see even here neighborhood midtown and they're not, so that makes me as well. So some neighborhoods, but we're not sure. To tell us which words have the highest C69 value and highest C12 value. Because high values of these were leading to high predictions. So what are the words that are commonly associated with high values of these? Maybe that'll give a sense about what these listings are, what's in the name that causes this high value, high price. So here what I'm doing is I'm saying, take those names we had and run word2vec on them, but don't aggregate them. So when we had aggregate method before, we said average. So take all the words in a listing and average the numbers. So we have one word embedding per listing. Here I'm going to say don't aggregate. I want to see the original word embeddings for each word specifically. And what I'm getting from this line of code is I'm getting the words and their C69 value, and I've sorted them by C69. So these are the ones that have the highest values, and at the bottom will be the lowest. So what we're seeing here is listings that have these particular words are going to have higher than average C69 value. Those are the ones that are getting the high price prediction. So if we take a look, we see it's professionals, view, Hudson, penthouse, views, multi-luxury. So these are all words that would probably indicate to us that this is going to be a higher price listing. We also saw in a surrogate decision tree that C12 was important, and high values of C12 were leading to a higher prediction. So let's do the same thing. Let's look at the words with the highest C12 values. So here we can see a lot of other things: midtown, terrace, pool, indoor, maybe indoor pool, roof deck. Again, all indicating probably higher priced or higher value listings. Now that I've done kind of this interpretability or this analysis of my data, maybe I feel more comfortable using this model in production. Maybe now I can even explain it to my team about what it found. So we don't have to necessarily use this model, but I can tell them the insights that were generated, and maybe we can come up with something from this. So typically in the workflow, just to wrap up, we usually do some data exploration, get a sense of my data, especially if this is a use case. Feature engineering. So how do I make this data usable to the model? How do I let it leverage all the information? Now the machine learning aspect, where I can build a single model, maybe I know what kind of algorithm I want to use, or I could do AutoML and let it try a bunch of different things for me. And then finally, I have my model, let me interpret it, let me make sure it makes sense. Could it tell me anything I didn't know about before? So that's a typical workflow. And then, of course, the last step would be maybe we productionize it. Maybe we download the Mojo and put this into some production environment and actually start using this model. And this is kind of just our demo for today. And what I like about, H2O-3 and this is that, again, I did all of this on my local computer on Jupyter Notebook, but I could have been working with millions, billions of records of data. And the work that I did would have been the same. So nothing changed. I could still make the same graph to show today. I could still do the same analysis, look at the same partial dependence plots. So to me as a data scientist, I'm not affected by the data side. I don't have to figure out how to handle it or how to sample down or did I do the sampling right? Because sampling in itself is a pretty complicated task, especially if you have imbalanced data or anomalies. So this is nice because I don't have to worry about all the extra stuff and I can just focus on my exploration, my analysis, my modeling, my interpretability. So with that, we have about 10 minutes left in our talk. So I'm going to leave it for questions and I'm going to have Patrick start reading questions out and we can go through the answers together.
Perfect. Perfect. Yes, absolutely, Megan. So we've got some great questions here. We'll try to get through most of them with time permitting. First question is, I'm looking to expose the Mojo model explanations, Shapley values in particular, at scoring time. Can you please advise on this?
Yes, so I believe our Mojo does have the Shapley values. I'm just going to confirm that while we're talking. Yes, it does. Okay, just double checked. Yes, so the Mojo has Shapley, and we actually have an example on our documentation. So let's go to our documentation right now. We go to H2O-3, and we're going to go to prediction. Well, you know what? It's Mojo, actually. Productionizing H2O. Let's see if it has contributions. Here we go. Here you go. There's a section on this. Enable contribution set to true. And here you get the Shapley reason codes calling Mojo. So this is just some Java code, like very simple. They're making a row object and putting the different features in. And it's calling predict. Since this particular setting, set enable contributions is set to true, you're also going to get the contributions out and you can print them out. But, it's very flexible. You can do it however you like.
Great. This question's come across a couple different ways, but is the link to the demo notebook, is that going to be made available after the presentation's over?
Yeah, let's do that. Let's maybe post it to the H2O tutorials repository.
Perfect. Okay.
So
yeah,
post it here.
We'll link to it. Yeah. Okay. Great. So yes, we will provide that after the presentation's over. Next question is, could you please talk about support for deep learning in H2O-3? Yes.
So you may notice we do have deep learning. This is going to be a feed-forward multi-layer neural net. So it's not convolutional neural net. It's not bidirectional GRUs. It's not RNNs. It's just kind of the standard, fully connected feed-forward neural net. So here, model, deep learning. There you go. So you can set the hidden layers, the activation function, and so on. And that's what we support.
Excellent. Next question, I'm going to combine two that are pretty similar. So first part of it is, so H2O Flow and H2O-3, are they free and open source?
Yes, so everything I just showed today is open source. The Flow, the Python client, the whole thing is open source. So if you go to H2O.download, you're going to see that there's an open source platform tab. You can click on latest stable release, and then you can download it however you like. So probably most of you guys are going to be doing R Python, so you could install an R, and it's just an install packages function. In Python, it's just going to be pip install. If you want to install it on Hadoop, it's really simple as well. You're going to do download the zip file, depending on your Hadoop version, and then you unzip it, and then you run a Hadoop jar command, and it really takes a minute. You'll be up and running. And once you run it, you'll get the flow information, how to connect flow. And this is also the IP and port if you want to connect to it from R Python locally. So really quick to get set up, and it's all there. And everything is open source. There's no closed source version of this product.
Great. So that actually segues into the next part of the question. So given that, what are what would you say are the main differences between H2O Flow and H2O driverless AI?
Oh, yeah, great question. So H2O Flow, or really we'll just call it open source H2O, the major differences are, there are two major differences. Open source H2O would offer you more control, typically. And control comes with responsibility. So it's not automated as much. You're going to select your model that you want to run, or do AutoML, but you're going to give it the parameters you want to do and so on. It doesn't do automatic feature engineering. So open source H2O doesn't do any automatic feature engineering like driverless AI. If we did driverless AI with this Airbnb data, it would automatically handle that text column for me, by itself. I wouldn't have to do anything. With open source H2O-3, I kind of had to tell it what to do. I was going to do word to vec. I was going to do data cleaning. So a lot more control, a lot less automation. The other major difference is that open source H2O-3 is written in distributed Java, which means it can scale. So you can run this on many, many machines and work with your full data set. Driverless AI does not scale. It only works on a single machine.
Okay, thank you. Next question is, when I use word embedding through word to vec, the word to vec algorithm, how do I know what each of the quote unquote C variables mean?
That's a really good question. Don't really mean anything. Nothing intuitive at least. They're just kind of a vector that's going to represent this. So C1 versus C2 doesn't mean anything so much. But what we did today was we tried to figure it out a little bit. So for example, we know that C69, if it's higher number, it has a higher price prediction. And you can even see this with the partial dependence plot. So we know that's the case. So one thing you can do is you can do a little bit of investigation. Like we did today, we looked at what particular words have the highest C69 value. So we can start to get a sense of what does C69 mean. So it looks like it was all related to words that most likely are indicative of a luxury apartment. So we can do that to kind of get a sense, but it's not going to be, these word embeds are not inherently intuitive. So it's not that C1 is going to mean location and C2 is going to mean size and C3 is going to mean amenity. It's not going to be like that. It's really going to be a combination of many things. So it's not interpretable completely. We can do a little bit like we did today to try to figure it out, but that's one of the issues. And if one of the things we are wanting to do is a completely interpretable model, what we probably want to do instead of doing word to vec is maybe building a model where we had a column per word, right? Does it say doorman or not? Does it say professional? Does it say view? So that would make it much more interpretable. It makes a very data set, so it's going to be a while to train, but it depends, I guess, on your use case and what your restrictions are.
Great. Next question is, can you visualize any Mojo object?
I'm not sure. I know we can do it for decision trees, so that would be gradient boosting machines, XGBoost random forest. Linear model, I don't know how we would visualize that, what it would really look like. So I would say probably not, but I would have to double check with our engineering team.
Okay, great. Is GBoost and XGBoost, are those models available on Windows also?
Sorry, what XGBoost, what was our algorithm, Patrick?
I think gradient boost.
Gradient boosting is available in all, I think XGBoost is as well.
Okay. And then is Shapley value importance, the global, is that the same as the model variable importance plot?
No, that's a good question. Oh, sorry, by the way, XGBoost is not available on Windows. GBM is. XGBoost is not. Yeah. XGBoost is only available on Linux and Mac. Okay, so, sorry, repeat that last question.
So, yeah, global Shapley value importance, is it the same as model variable importance plot?
No, it's not. So the variable importance plot is going to be dependent on the algorithm. So if it's a linear model, the variable importance is the absolute value of the coefficient. If it's a tree-based model, the variable importance is how much did the squared error reduce by splitting on that variable. So variables have high importance are variables where if I split on this particular column, it reduces the error when I predict. So we're actually using kind of algorithm-specific ways to get the variable importance. Shapley is kind of its own thing. You can definitely use it for variable importance. So we take the Shapley, the contributions matrix we were looking at before, and we maybe calculate the average absolute value for each one. We're going to get another way to represent variable importance. So there's multiple ways to look at variable importance, and you can definitely use Shapley to look at it, but it's not the same as what's coming out of the variable importance in the model.
Okay. Okay, so this is most likely going to be our last question. And so the question is, does the scalability in terms of size of the data apply when using the H2O-R package? I thought there were still RAM limitations, which used to say, for example, a requirement of 4 times the size of the data set in RAM to run on H2O GBM.
Oh, yeah. So we do recommend that you have about 4 to 5 times the size of the data in your H2O memory. But H2O does not need to be running where your R is or where your Python is. That's the main difference. So today's demo, I started H2O like this, which is going to start H2O on top of my computer. But as we saw before, we can actually download H2O and run it on Hadoop, calling this command, and it's going to give me an IP import. So what I can do is from R or Python, I can say H2O, R or Python, connect to this H2O cluster running over here, running in Hadoop. So you do not need to be restricted by the amount of memory on your local computer. If you have access to the other servers or Hadoop cluster or Spark, you can use that instead.
Okay, great. And I mean, one just came in that might be pretty quick to answer, but is model interpretation available for the R API?
Is model, sorry, what model what?
Model interpretation, is it available for the R API?
Oh, so, that really good question. So we did just do Python today, but everything that I did is available in R or Python. So,
excellent.
And most of it's also available in Flow. You can do variable importance in Flow. You can do the part dependence plots in Flow. So really the only thing that we did that would require some amount of coding was a surrogate decision tree at the end. But everything else you could do from Flow. And everything I did in Python, everything in Python can be done in R.
Great. All right, well, that'll do it for the questions today. I want to thank Megan for taking the time and doing the presentation. I'd like to say thank you to everyone who joined us today as well. The presentation slides and the recording will be made available on our Bright Talk channel in a few hours here. And we hope you have a great rest of your day.